Today we are building off the day where we were learning how to multiply binomials with algebra tiles. So typical questions that we've seen before are things like 2x plus 1 times maybe an x plus 2. So what this means is we can represent that 2x plus 1 with 2 x tiles and one single, a unit, and an x plus a 2, x, and two singles, two unit values. What is created is a product, an area, and this can be represented with an x times an x, length makes an x squared, and x times an x makes another x squared, and a few more x tiles. X times 1, x times 1 makes x, x times 1 makes x, x times 1 makes x, a few more, x times 1 makes x, x times 1, and then we have a few singles that are left over. So what we have is a final result, which we could say is 2x squareds and 1, 2, 3, 4, 5 x's plus 2. So we would write our final simplification as 2x squareds and 5 x's plus 2. Now what if, instead of being given the length and the width of this rectangle, this product, what if the length and the width were taken away and you were asked to create the rectangle? These would all be mixed up and you're being asked to make this into a rectangle. It is important to remember that when we are building these rectangles, they do have a very structured format where the x squared tiles go in the top left, the single tiles go somewhere in the bottom right, and then you have the x tiles that are vertical on the right, top right, and they're somehow horizontal in the bottom left. And you can have these in any kind of combination, but somehow we need to be able to put all this stuff that it creates a rectangle. That is our goal today. Our goal is factoring x squared plus bx plus c, where there is no number in front of the x squared other than 1, with algebra tiles. So it is quite an important concept to learn how to factor. The future of your math depends on it, and we are going to be using algebra tiles. So today you do need a set of algebra tiles, and using the algebra tiles, your task is to draw rectangles that represents polynomials. These are all 3 terms, trinomials. So we're tasked to make this appear as a rectangle. Now you might start by drawing, or you might grab your algebra tiles, and I'll start by drawing. What if you took an x squared, 5 x's? You could put one here, one here, one here. That's 3, 4, 5, and that means you'd have a whole bunch of singles, but there's only 2. In fact, there is no possible way to take these 5 x tiles and arrange them 4 across, 1 here, 3 and 2. There's no possible way to arrange these so that a rectangle with the correct number of units shows up. It is possible in some cases where it can. And in an example like this, we have an x squared, we have 4 x tiles, so I'm going to say a 1, 2, and we'll say a 3 and a 4, and then I have 3 singles. And this is what a rectangle looks like. It can be more clean if you even use your algebra tiles. So if we flip to a blank page, if I were to give you an x squared and 4 x's and 3 singles, could you make a rectangle? So the hope is that you could take your x squared and somehow line these up. Remember, your top right are vertical, your bottom left are horizontal, and somehow make it so everything fits. This didn't work, so if we move one up here and move one over here, There's your rectangle. And your factors are x plus 1, x plus 3. So ultimately the goal is to figure out what are your factors. Well, let's go back to our notes and remind ourselves of the difference. Last day we were continuing the idea of factoring, but there is still the idea of simplifying or multiplying. So two binomials multiply together to create a trinomial. X plus 3 times x plus 1 creates your trinomial. That's simplifying or multiplying. Factoring pulls them back apart and creates a product. It's very strange to see an x squared plus a 4x plus a 3 turn into a product, but it is possible. So, if you'd like to use your algebra tiles, great. Otherwise, you can follow along with sketches. Multiplying with algebra tiles. So, this is the forward direction. What if you're asked to simplify x plus 2 and an x plus a 4? So 4 singles. What is the result? Well, x times x, x squared. You have 2 x's in the top right. There are a whole bunch of x's in the bottom left. Please note that it's vertical top right, horizontal bottom left. And then we've got a whole bunch of 1 times 1s that are created. We also learned a strategy to do this with arrows and distribution, but the idea for multiplying will help with factoring. So we're left with an x squared, and we're left with 4 and 2 is 6 x's and 8 singles. Some people are actually pretty good at looking at the area and are able to see what your length and your width might be. There's a connection between the number of singles, 8, factors of 8, 4 and 2, 1 and 8, and that number that's in the middle. We'll come back to that. So factoring with algebra tiles. Try to make a rectangle to factor x squared plus 5x plus 6. Your task is to find an x squared tile, 5 x tiles, 6 singles, and place that in the area location with the x squared in the top left, singles in the bottom right, x's in the bottom left and the top right, and make it a rectangle. You can pause the video if you'd like to try, otherwise I will keep going. The result ends up working nicely if you have an x squared in the top left, 2 x's, and 3 x's in that spot. This will allow us to place 6 singles in the bottom right. Then we can ask what is the length and what is the width? Well, an x plus 2 and an x plus 3. Those are in fact your factors, and that is the answer to today's question. Factored x squared plus 5x plus 6 looks like an x plus a 2 times an x plus a 3. You have a few more to try. Example 1, example 2, example 3, example 4. These do get far more complex, so please after each video and give it a good attempt. I will continue with a final sketch for each and continue to pause as you go through the video. So we have an x squared, 7 x's. Ooh, 1, 2, 3, 4, 5, 6, and then a single down here, a single x, and 1, 2, 3, 4, 5, 6 singles. There's a rectangle. X plus 6, x plus 1 is what we would write as our final answer. X plus 6, x plus 1. Some people start to see the solutions before they even start using their tiles. Now this one's a little bit trickier because what we've got is an x squared, 6 negatives, and 1 negative x. This almost warrants going and doing a full attempt together. We have an x squared, a negative x, where the white side is the negative, and 6 negative tiles. 1, 2, 3, 4, 5, 6. So somehow we have to make a rectangle out of this. We're seeming to have not a lot of choice. Rectangle not being created very nicely. Well, there is something that we can actually do very, very sneakily, is I'm going to introduce at the bottom here 2 x tiles. One's going to be negative and one's going to be positive. Their value is 0. So if I place these on the page, they do not affect this expression. But I'm going to place them in locations where they're both together, so negatives are together and the positive is on its own, and see if I can start to make a rectangle out of this. Well, what if we introduce another set of 1 negative, 1 positive? And all of a sudden, it's possible to create a rectangle. Dimensions in this case are positive x plus 2, positive x minus 3. So, going back to our sheet and doing a quick sketch in our notes provides us with 2 positives. I'm going to use shading to represent the negative, so there's less to shade. There was a negative, there was a negative, there was a negative, and together those made the negative x, and then a few negative tiles, which we get to call our negative 6. And as we continue, x squared minus 5x plus 6, again, you gave this a solid attempt, and we can check an x squared, 5 negative tiles. There's 2 negative ones. There is 2, 3, 4, 5 negative x's in total, and these ones are positive singles. How is it possible to create these negatives mixed up with these positives with these negatives? Well, if we put an x tile that's positive, and we put some negative singles, a positive x tile, and some negative singles, we can check. Positive, positive, positive. Positive, negative, negative. Positive, negative, negative. Negative, negative, positive. And that's why it works. So your factors end up being an x minus 2 and an x minus 3. And we have an interesting case as well, an x squared minus 4, an x squared and 4 negative tiles. And the result we'd have with this one, only way this is possible is if we have 2 positive and 2 negative, which cancel out all the x tiles. That's why there's only an x squared minus 4x's. So your factors are x minus 2, and for the top one, an x and plus 2. This does take some time to practice, and it's not an easy thing by any means, but it does take practice. Last thing, it's interesting if you could create a question that is factorable. So you might take some algebra tiles, create a rectangle, and there is your question. A partner can solve your question. Don't let them see your answer though. So you might take a moment, try to see if you can create a question, create an area that is factorable, and have them attempt it. And for example 3, the last one, factor by any approach. This one is listed here because there's actually a 3, a 12, and a 9, and there's actually a greatest common factor that we learned last day that allows us to take out a GCF. And then once we're done, we're able to use our algebra tiles and factor this trinomial the new way. And with a little bit of time, you will get good at seeing these very, very quickly. So often, you're going to see GCF factoring mixed up with our algebra tiles and trinomial factoring. Today's practice is from page 166. Number 4, 5AB, 8A, and number 10. We are using algebra tiles to factor. Moving forward, we learn strategies to factor without algebra tiles. Good luck.